Hello, this is 9.3a, domain and range, and asymptotes of rational functions. Okay. In general, we want to be able to identify domain range asymptotes of a rational function given its equation. So first off, domain and range, we're primarily going to focus on domain here. Okay, you don't have to worry about range really at all for me. Domain is all possible x values, range is all possible y values. We already know that. For a rational function, we need to remove values that make the denominator equal 0, right? Because a rational function is like a fraction and division by 0 is undefined, we need to remove x values that would make the denominator become 0. And then for range, best way to identify range is just to look at the graph and see what are the possible y values. All right, for all of this, I'm going to request that you use interval notation because that is something that we want to get in the habit of using. So let's just practice stating this domain in interval notation. All right, first you want to make sure that you know what makes the denominator equal 0. We want to know what makes the denominator equal 0. What makes the denominator equal 0, okay? This is a quadratic. In order to solve a quadratic, in order to figure out what makes that equal 0, we have three options. We can either use the quadratic formula. We can either factor, or we could complete the square. For most of these, they're probably going to be factorable, okay? Because there's so much work involved with rational functions. Adding in extra steps of quadratic formula or completing the square just feels like a lot. So typically you're going to be able to factor here. X squared plus x minus 30 will factor into x plus 6, x minus 5, meaning that x plus 6 equals 0 and x minus 5 equals 0. So when x equals negative 6 or when x equals 5, that causes this denominator to equal 0. So we need to remove these from the domain. Okay, so if you think about a number line, right, a number line, say that negative 6 is over here, then 5 is here, 0 is somewhere in the middle. Okay, we are totally good to plug in any number to this rational function up to negative 6. Then we want to skip over negative 6. And then we want to keep going, keep going, keep going, keep going, keep going, keep going, keep going until we get up to 5. And then we want to skip over 5, right? So this little region in between is fine. And then after 5, we can keep going, okay? So we can represent this in interval notation, right? This region 1, 2, and 3 are going to be 3 different intervals that we want to connect using union symbols. Okay, so that first region is negative infinity up to negative 6. We want to use parentheses because negative 6 is not included. We want to include the region between negative 6 and 5. Parentheses again because those numbers are not included, negative 6 and 5. And then we want to go from 5 up to infinity. And we need to put union symbols in between in order to be in proper interval notation. So this is our domain. All right, consider this one. What would make this denominator equal 0? Let's factor that denominator just to see so that it's much more straightforward. All right, and then looking at this denominator, what makes this denominator equal 0? X plus 6 equals 0, and then x minus 2 equals 0, right? So whenever x equals negative 6 or whenever x equals 2, that causes the denominator to be 0. So we need to remove from the domain those values. Okay, again, going back to your number line, right? Negative 6 is here, 2 is somewhere up here. We are fine up until we reach negative 6. We are fine after negative 6. And then we are fine after 2, but we need to skip over those values. So in interval notation from left to right, we go from negative infinity up to negative 6, parentheses on both ends, union, and then they have the value in between. Remember with interval notation, we always want to go from least to greatest on left to right. All right, it's very important that your negative infinity comes first, then your negative 6, then your negative 6 and your 2. You should not, do not write You should not write this. That's improper. Okay, 2 comma negative 6. Don't do that. Don't do this. That's improper. Don't do this. That's improper. Okay, infinity is bigger than 2. 2 is bigger than negative 6. Negative 6 is bigger than negative infinity. So we want to write in order like this for our domain. One more domain problem. Let's factor both the numerator and the denominator. It's good practice, to be honest. Okay, this numerator factors into x minus 8, x plus 1. And then this denominator factors into x minus 9, x minus 2. What makes this denominator equal 0? Here and here. 9 or 2, right? Think about your number line. 2 is here, 9 is here. What values are okay? Everything's fine, up to 2. Skip over 2, go up, 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 up in between 2 and 9. Skip over 9, and then keep going, okay? So negative infinity up to 2, and then in between 2 and 9, and then from 9 up to infinity. That's your domain. Those are your possible x values. All right, next piece with rational functions. Okay, this section, this is the first half of 9.3. We are building the foundation for how to graph rational functions by hand. Okay, and rational functions have these special things called asymptotes. So do logarithmic functions, which and exponential decay functions. Okay, we've seen asymptotes before. All right, asymptotes are dotted lines that graphs of functions get really, really, really close to. Okay, that's the best straightforward definition that I can give you. For rational functions, it is possible for, so generally rational function graphs look something like this, roughly. Okay, they got these fun little curves. You can call them like a little skadoosh if you'd like. A vertical asymptote would then be this vertical line that we are approaching. There's also such thing as a horizontal asymptote, which we'll get to in a second. In order to find your vertical asymptotes of a rational function given its equation, you will do this first step. Set the denominator equal to 0 and write the asymptote as x equals a number. Okay, it is possible for there to be no vertical asymptote. There can be multiple, there can be none. The graph cannot cross the vertical asymptote. Okay, horizontal asymptote. So back to this picture again. There's also here a horizontal line that we are getting very, very close to. Okay, and these have some rules that we really just gotta get familiar with. Okay, a horizontal asymptote, we will abbreviate it as HA, is a horizontal dotted line. Rational functions may only have one at most, so there will not be multiple horizontal asymptotes. To figure out what it is, what the equation of that line is, look at the exponents of the numerator and the denominator. And here are 3 rules that you're probably going to refer back to your notes a lot until you get comfortable doing this. Okay, if the numerator degree is greater than the denominator degree, then there's no horizontal asymptote. There's something called a slant, which we will look at in the next section. If the numerator degree is less than the denominator's degree, then this is your horizontal asymptote, y equals 0. Very straightforward. If the numerator's degree is equal to the denominator's degree, then the horizontal asymptote is the ratio of the leading coefficients. And graphs can cross a horizontal asymptote, and we will see some examples like that throughout the next section, 9.3b. So we're going to look at an example of each of these 1, 2, and 3 cases. Okay, here's the first case. So let's state the asymptotes for this function. Okay, vertical asymptotes. Remember, you're going to set the denominator equal to 0. 2x minus 1 equals 0. 2x equals 1. X equals 1/2. So this graph, if we were sketching it, we would have a vertical line, vertical asymptote, right here. Okay, approximately at x equals 1/2. Horizontal asymptote, look at the degree and then follow your exponent rules. So here we have, when I say degree, I mean the highest exponent in the numerator and the denominator. Okay, this is x squared. This is x to the first. So here we have a case where the numerator's degree is greater than the denominator's degree. So this is like case number 1 right here. Numerator's degree is greater than the denominator's. There's no horizontal asymptote, none. Okay. Second case, if the numerator's degree is less than the denominator's degree. Again, for our vertical asymptote, you're always just going to set your denominator equal to 0, and then the horizontal asymptote is where you look at the degree. Okay, vertical asymptote, set negative 3x squared minus 3 equal to 0. We're going to solve this out. Negative 3x squared equals 3. X squared equals negative 1. So what number squared equals negative 1? There are no real numbers that satisfy this. There's only imaginary numbers. So we would not be able to graph that on a coordinate plane. So there is no vertical asymptote here. Okay. And then looking at our horizontal asymptote, our numerator's degree is 1. That is less than the denominator's degree of 2. So looking at your exponent rules, this is case number 2, where the numerator's degree is less than the denominator's degree, meaning the horizontal asymptote is y equals 0. Okay, so if we were looking at this graph, there would be a horizontal line that this graph would not, this graph would get very, very close to it and potentially cross. Okay. Final case, if the degrees are equal, again with that vertical asymptote, we're just going to set our denominator equal to 0. Horizontal asymptote, we will look at the degree. Okay, 3x minus 9 equals 0. 3x equals 9, meaning x equals 3. You need the x equals there because otherwise we don't know whether it's a vertical or a horizontal line. Okay, you need an x equals 3. You need the x equals 3, meaning if we were looking at this graph, we would have a vertical asymptote around here. X equals 3. Horizontal asymptote, look at the degrees. Notice that this is a degree of 1. They both have a degree of 1. Because they have the same degree, we look at the ratio of the leading coefficients. The ratio of the leading coefficients. So the numbers that are being multiplied by the x, we take the ratio of those. Okay, negative 6 and 3. We just divide them like this. Take the numerator's coefficient, divide it by the denominator's coefficient. Negative 2. Okay, because this is a line, it's a horizontal line, we need to put a y equals with it. Y equals negative 2. So there would be a horizontal asymptote like this. Okay. All right, let's try this. Let's consider stating all of the following for this function, all right? Vertical asymptote, we've been doing this. We're going to set our denominator equal to 0. Horizontal asymptote, we're going to look at the degree. For domain, we're going to remove values. Remove x's that make denominator equal 0. That make the denominator equal 0. All right, and then x-intercepts, y-intercepts, we have found them a million times. You might have forgotten. For x-intercepts, you just set y equal to 0. Or in this case, we're just going to set the entire function equal to 0. Okay. And then this is actually going to result in just setting your numerator equal to 0. Set numerator equal to 0. Okay. For y-intercepts, you're going to plug in 0 for x. Okay. So let's find our vertical asymptote first because that's what we're most comfortable with. We've just been doing it a ton. We're going to set that denominator 2x squared plus 7 equal to 0. 2x squared equals negative 7. X squared equals negative 7 divided by 2. There is no number that we can square that will give us a negative number, so there's actually going to be no vertical asymptote here. For your horizontal asymptote, look at the degree. We have the same degree as both 2. This leading coefficient is a 1. Because they're the same degree, we need to look at the ratio of the leading coefficients. 1 divided by 2, and because this is an asymptote, it's a line, we need y equals with it. It's horizontal. That's what tells us it's a horizontal line. For our domain, remove values that make the denominator equal 0. Guess what? We also use that process for the vertical asymptote, and we found that there are no values that make the denominator equal 0. So the domain is all real numbers. There's nothing that we have to remove. That just leaves our asymptotes. The y-intercept is typically very straightforward. You're just going to plug in 0 for your x's, so 0 squared plus 2 times 0 plus 1 divided by 2 times 0 squared plus 7. 0, 0, 0, 1/7 is your y-intercept. Write that as a coordinate over 0 up 1/7. And then your x-intercept, we're going to, it's really like we're setting the entire function equal to 0, right? We're setting y equal to 0, so 0 would equal x squared plus 2x plus 1 divided by 2x squared plus 7. And in order to start solving this, you would multiply both sides by that denominator. But really, when you take 0 times that, it just cancels out, so it's really just like you're setting the numerator equal to 0. Okay, so 0 equals x squared plus 2x plus 1. To solve this, we have three options: factor, quadratic formula, or complete the square. Typically, you're going to be able to factor with ones that you're given here. This factors into x plus 1 times itself, meaning x equals -1. So our y-intercept is -1, 0. Okay, so this section is just getting comfortable with the algebra of these pieces, and the next section we will actually look at graphing them.